So this topic is still about the phasors diagrams, phasors diagram. And this time we're gonna take a slightly more complicated circuit than the last one. Anyway, let's start by assuming that we have a voltage supply, an AC voltage supply like so. And we're gonna write Vs of t, this is the voltage supply, supply in 10 volts, sine 100t plus, I don't know, 40 degrees. That's Vs. Now let's say that it feeds into a resistor whose value is exactly 100 ohms. So this is R. And we're going to put in here an inductor. It could have been a capacitor, by the way, the logic is the same. And let's say that the value of the inductor is 1.5 henries. All right? Let's say that the question is, what is Is of t? That means, what's the current? What's the expression of the currents that flows in here? What is VR of t? Which means let's find the voltage across here, the resistor, I'm sorry. And then VL of t, this one is actually the inductor, and we want to find the voltage here across the inductor. So we want all of these. And then we want to draw a phase diagram to see how everything relates to everything. All right? Well, instead of doing the analysis in the time domain, we're going to go to the phasor domain. So this is the time domain. So what I have in here is the time domain. That means the voltages and the currents and everything, they depend upon the time. And now we're going to switch everything to the phasor domain. So here's what happens in the frequency or the phasor domain. In the frequency of the phasor domain, here's pretty much what happens. The voltage supply will be replaced with something we're going to call Vs. The resistor will be replaced with an impedance, ZR. The current through the circuit will be replaced with a phasor Is. And the inductor will be replaced with VL. Now the question is, what are these parameters? Well, it's not too complicated. This one will be unknown for now, but these, we definitely can find them fairly easily. Let's start with the simplest of the two, which is Vs. If I go back to the expression of Vs, the maximum is 10 volts, and the phase shift is 40. So we can very easily simply say that in the phasor domain, Vs is 10 volts, and the phase shift for that one is 45 degrees. Was it 40 degrees? 40 degrees. So 40 degrees. All right, ZR is pretty simple. The value of ZR is 0. The angle is always 0, and this is nothing but R. And what's the value of R in our circuit? 100 ohms. So in the phasor domain, ZR is simply 100. I don't know what happened in here. Why did the color change? It's 100 ohms with 0 degrees. ZL is also not very complicated. It's the reactance of the inductor and plus 90 degrees in here. Now, what is the reactance of the inductor? L times omega plus 90 degrees. Let's plug in the values. L was 1.5 henries. So it's 1.5 henries. And omega, if we go back to the expression of Vs. Here's omega, it's 100. This is omega. So it is 100 times 100, and the angle is plus 90 degrees. So it's 150 ohms, and the angle is plus 90 degrees. Furthermore, this is a very simple series circuit. And remember, impedances follow the same rule as the resistances. So we can now come back and simply say that the same voltage supply giving us the same current, Is, is feeding into one impedance, we're going to call it ZT, which is simply ZR plus ZL. All right. Now let's find out numerically what ZT is. ZT is ZR plus ZL. All right. ZR is 100 ohms, obviously, with an angle of 0 degrees, plus ZL was 150, if I'm not mistaken. Yeah, 150 with an angle of 90. All right. Now, there is no easy way to do this, so what I'll have to do is just switch on my trusted calculator and just plug in the numbers. All right, so the first one is 100. Oops. 100 with an angle of 0. By the way, when you have 100 and an angle of 0, you can simply put 100 plus, and the other one is 150 with an angle of 90. All right, so what's the end result? All right, we get some weird stuff. So 180.28.3, 56.3. All right, so ZT is 180.3. I rounded, by the way. This is in ohms. And the angle is 56.3. All right, so sorry, I got interrupted by a phone call. Anyway, so ZT is 180 and the angle is 90 degrees. Now that we have ZT, according to Ohm's law, the voltage across ZT, we're going to call it VT, and Vs are 100% the same. Reason is very simple. There's a wire here, so no drop of voltage. There's a wire in here. Okay, so we can simply say that according to Ohm's law, Vt is the voltage across that ZT equals the impedance itself times the current that flows through it, which is Is. Why Is? Well, because there's only one component, and that's the current that flows through it. Now Vt, we can replace it with Vs, because they are the same. So it's equal to Zt times Is. Now, this, we just calculated it. This was given at the very beginning, and this one we can find it. All right, so Is is Vs over Zt. Vs was 10 volts, I think, and the angle was plus 40 degrees. Zt was 180.3 ohms with an angle of The angle was not plus 90. What am I saying? The angle, sorry guys, I got interrupted. 56.3. Right, so this angle here, I made a mistake. Right, I got interrupted by a phone call, and when I came back, I recorded the wrong value. The angle is 56.3 degrees. Okay, so I come back in here, and the angle is 56.3. Let me double check on my calculator. Yes, it's 56.3, 180.3. This 3 is rounded. It's 2789 some change. All right, now I'm going to switch again to my trusted calculator. All right, so I'm going to clear everything. All right, start on a blank slate and simply tell it that I need 10 with an angle of 40 degrees, obviously. This is to be divided by 180.3 with an angle of 56.3. Now, we already know that the angle is going to be negative because we have to subtract 56.3. So the difference of angle will be minus 16.3. So that much I already know. Now the rest. All right, so it's 0.05546. So IS is 0.055. How much is it? 0.055463. And the angle is negative 16.3 degrees. Now 55.4, we can round it to 55.5 milliamps, but let's just leave it the way it is. So these are amps, by the way. All right, so we got IS now. And remember, the question is, if you have, what is IS of t? So now IS of t is extremely simple. Here's the 0.0555. Just rounded the 463 to 5. This is amps times sine 100t minus 16.3 degrees. This is I of t. But it's not the only thing that we wanted. We also wanted to VR of t. All right, so if we go back to this circuit here, this one here, what's the relationship between VR, which is the voltage across ZR, and IS? Well, VR, this is the phasor VR, it's ZR times the current that flows through ZR, which is in our case IS. ZR was 100, and the angle was 0 degrees, if I'm not mistaken. And then IS is 0.0555, just rounded to 55.5, and the angle was negative 16.3, if I'm not mistaken. Yes. So now this is VR. VR, 100 times 0.0, it's 5.5. So 5.55 volts, and the angle is negative 16.3 degrees. If I have the phasor VR go from the phasor domain to the time domain, VR of t is 5.55 times sine 100t minus 16.3 degrees. And finally, VL. So in the phasor domain, VL is ZL times IL, but IL here is simply IS. So we just need to find ZL. I don't remember the values, so where is ZL? ZL was 150 with an angle of 90. So ZL is 150 ohms, obviously. You have a plus what? 90 degrees. And IS is 0.0555, angle of negative 16.3 degrees. So this would be VL, 150 times 0.0555. I'm going to turn on this thing. Clear everything. So 150 times 0.0555, that gives us 8.325 volts, obviously, and the angle was 90 minus 16.3, so 90 minus 16.3, that gives us 73.7. So the angle here, 73.7 degrees. We convert this to the time domain. VL of t is 8.325 sine 100t plus 73.7 degrees. All right, now that we found all of this, let's now do the phasor diagrams, or phasors diagrams. So we're going to now do one last thing. We're going to draw a phasors diagram. All right, so here it is. This is the imaginary axis. Trust me, guys, it's not that easy to draw a horizontal line with this thing. All right, this is to the best of my abilities. I mean, vertical line, horizontal line, not too complicated. So this is the imaginary axis. This is the real axis. Now let's start putting all the different diagrams. First, VS. VS is equal to 10 volts and 40 degrees. Right, this is 90, this is 45. 45 cuts this angle into equal halves. So it's all like this. That's exactly 45. So this angle here is 40 degrees. And this magnitude here is 10. So this represents VS, the voltage supply. We found IS to be 0.00555 negative 16.3. So here I'm going to exaggerate the size of IS. IS is 0.055 and angle of minus 16.3. So this is IS. I am highly exaggerating its size. The magnitude here, the length from this edge to this edge is only 0.0555. So this is going to be IS. Right? The angle is negative 16.3. All right, so 40. This is almost like 56. The difference between this one and that one is 56 degrees. So that's IS in red. Now, VR, I'm going to put it in blue, would be 5.5 and minus 16.3. So VR would be along this line here. This is VR. Now, notice an interesting thing. The angle is also negative 16.3 degrees. That means VR and IS are in phase, which means that there's no difference of angle between VR and IS, which is what we expected. If you remember what we said, ZR is R with an angle of 0. This is the angle that the current and the voltage make. All right, so this angle is angle between IR, current that flows through IR, and VR. Now, IR is IS. This is very simple, the same current. So in our circuit, we could say that IS, the current flowing from the source, is the same as the current flowing through the resistor, and is also the same as flowing through the inductor. So they're all the same. So IR and IS are the same, so I would expect IS and VR to have an angle of 0. And lo and behold, that's the case in here. This is minus 16.3, this is minus 16.3. So this squares with everything that we said all along. Okay? Now, VL. VL is 73.7. So I'm going to use a completely different color, maybe some kind of green or something. This is VL. This is 73.3. So this, oops. This is VL. VL makes with this thing 73.3. Now, what did we say about ZL? ZL is XL with an angle of plus 90 degrees. And what does the plus 90 degrees simply mean? The plus 90 degrees, that means that IL and VL are at 90 degrees of each other. This is really what this number means. That means the current through an inductor and the voltage through an inductor should have a 90 degrees between them. Now let's see if that squares with everything we've been saying here. If this is 73.3, okay, and from here to here, and this is IS. Remember, IS is the same as IL is the same as IR. So if I take IL, there's a minus 16.3 and there's 73.3. If I take 73.3 and add to it, I mean 73.7, I think. 73.7, I'm sorry, it's not 73.3, it's 73.7. If I take 73.7 and 16.3 and add them up, ta-da, 90 degrees. So from this current here all the way to here is 90 degrees. Right, the diagram is getting kind of messy, but that's pretty much it. So I have VS, I have IS, I have VR, and I have VL. Everything is drawn in this diagram, and everything squares. The angle between VS and IS is 40 plus 16.3. So the angle between VS and IS is, I got 40 degrees going up and 16.3 coming down. So it's 40 degrees plus 16.3, so it's 56.3. So in this particular case, there's a 56.3 angle between these two guys. All right. If I go from here to here, this is 56.3 degrees. And this is what we call a Phasor diagram. Now, there's something in here that, technically speaking, if everything was done to scale, I would have found out, and this is it. If things were done properly, then I would have found out that VS is VR plus VL. Or in other words, if I take the algebraic sum of VS minus VR minus VL equals 0. In other words, KVL applies in AC in both time domain and Phasor domain. By the way, the Phasor domain is what we call the frequency domain, but I'm just going to start calling it the Phasor domain. In a different class from a 300 level 345, if I ever see in there, then we're not going to call it the Phasor domain anymore. We're going to call it the frequency domain. And you'll understand why it is called the frequency domain through the Laplace transform. So KVL does apply. KCL also applies. In AC in both time domain when we do the time domain analysis and Phasor domain. So the theorems that we have seen before, they also apply 100% in here. Now, this one I'll have to prove it later on, but I just wanted to go a little bit ahead of myself. And now, based on this example, we should be able to do, I don't know, RC series or maybe even RLC. And by the way, RLC is as complicated as it gets. All right. Okay, so I'm going to stop the video here and then send it your way.